Okay, we're back here working on some time value money questions. We've got this worksheet. In the previous video, we've worked problems 1 through 4, and in this video, we're going to work problems 5, 6, 7, and 8. Okay, so we're going to work problems 5 through 8 in this video. We're going to start with problem 5, and this is similar to the problem that we first discussed in the first video on time value of money. Remember from that video, your parents loved you and they invested $5,000 into the S&P 500 index fund that pays 12.5%. And then we wanted to see how much that $5,000 investment would be 65 years later when you go to retire. And we found that I can't exactly remember the number, 10.5 or $10.6 million. That $5,000 investment, if you invest in the S&P 500 and get 12.5% per year, it becomes about $10.5 million at your 65th birthday. Here, we suppose that your parents invest $5,000 the day you're born into the S&P 600 index, which pays on average 17.4% per year. Let me explain. So this is on CNBC. This is the S&P 600 index. Now, the S&P 500 index consists of the 500 largest stocks. The S&P 600 index consists of the 600 smallest stocks that are publicly listed on major U.S. Stock exchanges. So a couple of things to note. The S&P 600 stocks are you've never heard of these stocks, right? And these stocks are much more volatile than the S&P 500 stocks. They're much more risky, and therefore they have a higher return, okay? So generally speaking, the S&P 600 small cap index is much more risky, but it also pays a higher return. Over the last 90 years or so, the S&P 600 has averaged 17.4% per year. So question number 5 is similar to the first question we asked, but instead of getting 12.5%, we're getting 17.4%. We want to see how much this account will be worth when you retire on your birthday at age 65. Okay, so let's go ahead and do this. On the financial calculator, we're going to invest $5,000. That's an outflow. Okay, so that's going to be a negative outflow for us. So I'm going to enter that into the present value function. And that's the only amount that I'm going to put into this account. Zero payment. So I'm going to say zero payment. There's a zero reoccurring investment payment here being made. Of course, we're solving for future value, what this amount's going to be worth 65 years from now. And in the financial calculator, I'm going to use percentages when I enter my interest rate or my rate of return. So 17.4 I over Y for 65 years. Enter that into the time function there. And then I'm going to compute future value. Look at that. So the future value of earning 17.4% per year for 65 years on a $5,000 investment is $168.8 million. All right. So that's important to understand. We were getting $10.5 million if we invested in the S&P 500 index fund. Here, if we invest in the S&P 600 index fund and earn 17.4%, just 4% more per year, look at what happened to the future value. In Excel, I'm going to say equals future value. I'm going to use this future value function. My rate in Excel is going to be 0.174. Recall in Excel, I use decimals. Number of periods is 65. Payment is 0. Present value, again, negative 5,000. And compounding at the end of the period. Okay, I'm going to close my parentheses there. I'm going to hit enter, and it should be the same as what we got on the financial calculator. And there you see it, 168.8 million. All right, so that was question number 5. What we learned from that question is that 4% per year matters a great deal when we're talking about long-term investing. Okay. Question number 6, what we're going to learn here in number 6 is how frequently the interest compounds also matters dramatically. Okay, so look, what if the interest in this retirement account compounded monthly instead of yearly? How much would the account be worth on your 65th birthday? So this is super important. So up till now, we've just assumed that any interest that is compounding on this retirement account is compounding at the end of the year one time per year. Now what we're saying is what happens if the interest is compounding every month? So instead of getting a one-time interest payment on our account that then compounds the next year, what if we're getting smaller interest payments that are happening monthly, but that compounding is happening more frequently. Okay, in order to do this, we've got to do a couple of things here. First, we've got to figure out how many periods there are, how many months there are in 65 years. Okay, so what we're going to do is I'm going to take 65 and I'm going to multiply that by 12. Okay, so there's 780 months. So how I'm going to change this problem to account for monthly compounding instead of annual compounding is I'm just going to change all of the inputs into monthly terms instead of annual terms. So 65 years becomes 780 months. I'm going to say enter that into the time function here. Okay, 17.4% per year. I'm going to divide that number by 12 to get a monthly interest rate, and I get 1.45%. I'm going to enter that here into I over Y. Now notice the present value doesn't change. I don't have to divide my present value by 12 or times it by 12 here. My present value remains the same and my future value remains the same. So anytime you're dealing with compounding at a frequency of greater than once per year, the functions that you change is the time function and the rate of return function, and we'll learn in later problems in later videos that we need to also change this payment function. However, present value and future value remain the same. So I'm going to enter in negative 5,000 present value. Okay, payment is still 0. I'm going to compute future value here, and I should get something much greater than 168 million. Look at what happens. So if interest compounds monthly instead of annually, then that 168 million that we were getting with annual compounding becomes 376 million when we account for monthly compounding. Okay, the question that probably comes to mind is if you did invest in the stock market, what does interest compound annually or does it compound monthly? It actually compounds continuously, instantaneously. Okay, but we're going to talk about that when we answer number 7 here. We're going to talk about how the effect of the frequency of interest compounding changes. Okay, let me solve for this in Excel just so you have it here. I'm going to say equals future value. My rate of return was 1.0145. That's 17.4% divided by 12. My number of periods was 780 months in 65 years. Payment is 0. Present value is negative 5,000. Compounding at the end of each month, the end of each period. Close my parentheses. And again, I get 376,331,000 and some change. Okay. So what we learn is interest that compounds monthly instead of annually leads to a much higher future value. Okay. Let's now answer number 7. Okay. What happens if interest in your retirement account compounds daily instead of yearly? How much would the account be worth on your 65th birthday? Okay. So now it's compounding daily instead of annually. We've got to change. We got to change the years into days. So I'm going to take 65 times 365. Okay. That gives me 23,725 days. I'm going to put this over in Excel here because I need to remember these numbers. Okay. And now I've got to take the 17.4% per year and divide it by 365. And I get 0.0477%. Okay. And now I can go about solving the problem here. So I'm going to say 0.0477 I over Y, 23,725. Enter that into the time function. That's the number of days. Negative 5,000 present value, 0 payment. Compute future value. Before I do, let me ask you, do you think that the future value is going to be greater or less than this number? All right. And not only is it going to be greater or less than this number, by how much? When I hit compute future value, look at what happens. Notice that it is greater, right? The interest is compounding more frequently, so it should be greater. But notice that as it compounds daily, the increase from annual to monthly was much greater in future value terms than the increase from monthly to daily. Okay? So what we learn is that the relationship between the frequency of the interest compounding, the relationship between the frequency of the interest compounding is increasing, but it's increasing at a decreasing rate. As we go from yearly to monthly, we get a huge jump in future value. As we go from monthly to daily, we get a much smaller increase in future value. As we go from daily to continuously to instantaneously, it's much, much smaller. Okay. And so when we talk about interest compounding in the stock market in real terms, compounding continuously, I mean, you're getting a pretty good estimate of what the future value is going to be if you do monthly or do daily. Does that make sense? So let's do this here in Excel so we have it. Future value is equal to 0.00477. Notice I put that in decimals. I need one extra zero there. 0.00477. So that's 0.0477 in percentages, but I put it in decimal terms. 23,725. Payment is 0. Negative 5,000 present value. Compounding at the end of each day. You should get something very close. Okay, does that make sense? So number 7 gives us a better approximation of what would happen if we accounted for daily compounding. And let's conclude this video by answering number 8. How many years will it take to become a millionaire if you invest $5,000 today into an account that pays 12%? Okay, so this is a pretty straightforward question. Again, first thing that you need to ask is, first of all, what are we solving for? Okay, and you can see in problem 8, how many years will it take? So we're going to solve for n here, the number of time periods. Will it take to become a millionaire if we invest 5,000? So the next thing that we look for is, what is the outflow? And because we're investing 5,000, that's going to be a negative 5,000 in the present value. We want to have $1 million as a future value, and that's going to be an inflow. That's going to be positive, and it's paying 12% per year. So on this problem and on the problems that follow, anytime I don't list how frequently the interest is compounding, let's just assume that it's compounding at the annual rate. At the annual rate, yeah. So let's solve this here. So 5,000 negative outflow investment goes into the present value function. And I want to see how long it will take me to become a millionaire. So I put positive 1 million into the future value. Payment is 0. I over Y is 12%. And I compute N. In order for $5,000 to turn into $1 million, it's going to take 46.75 years. To solve for that in Excel, I say equals NPER. That's the number of periods at a rate of 0.12. Payment 0. Present value negative 5,000. Future value 1 million. Compounding at the end of each year. Let that sit for a second. Close my parentheses. I get 46.75 years. Okay, so this tells us that it takes a long time. Remember, this is similar to the very first problem on the first video that turned into over $10 million. What we're saying is it took almost 46 years to turn that $5,000 into $10 million or into $1 million, and then it takes the rest, the 19 years after that, to turn it into 10 million. Okay, so we've learned a couple of things here regarding time value of money. First, we've talked in this video about how interest compounding more frequently is going to increase the future value, but it's going to increase it at a decreasing rate. We've also talked in problem number 5 about the S&P 600, how important 4%, the difference between the S&P 600 return and the S&P 500 return, that 4%, how much that matters for long-term investing. And now we've also talked about how the future value begins to increase. So it took 46 years to turn $5,000 into $1 million, but it only takes another additional 19 years or so to turn that $1 million into $10 million. Okay. Good. In the next video, we'll come back. We'll answer a few more questions. Hopefully, this is going to be helpful in helping us understand time value of money.